of the webinar so you could watch it again if you loved it the first time. Anyway, we'll be getting going here. My name is Neil Paulhemus. I'm in charge of development of Statgraphics. And today I've got a very interesting topic to talk about, and that is using Statgraphics Centurion to do an analysis of variance. Now this will be the last webinar in our spring series, what I've been calling the spring series. Although if you're anywhere near Washington, D.C., which is where I am, you know that it's certainly the middle of summer, with temperatures actually over 100 degrees Fahrenheit yesterday and maybe a little bit cooler today. But this is still what we're calling the spring seminar, spring webinar series. After this webinar, I'm going to take a little bit of a break, and then we'll start back up again in the fall, talking about some other topics that might be interested to folks who use Statgraphics. Now, during the course of this webinar, you have the ability to send us questions. We'll be monitoring whatever questions you send to us during the broadcast. And at the end, they'll give me a summary of the questions that came in, and I'll try to cover as many of those as I can. Okay, you can also, if you would, thinking ahead to the fall, let me know if there are other particular topics that you'd like to see covered that I have not covered here in the spring. I'd be happy to cover any topics of interest. I know we haven't done anything in terms of time series analysis. We haven't done any sort of reliability or life data analysis. So those are a couple that come to mind immediately for me, but I'd be quite interested in knowing other topics that you all would be interested in hearing. As I said, the topic of today is using Statgraphics Centurion to do an analysis of variance. Very important topic, obviously a very heavily used section in Statgraphics as it is in most statistics packages. Now when I talk about an analysis of variance and analysis of variance models, I'm talking about statistical models that look at a response variable, some response variable that I'm interested in, and partition the variability in that response variable into components that can be attributed to one or more explanatory factors. There may be just a single factor. If you're doing a one-way ANOVA, there could be quite a number of factors in a more complicated design. Now, most of the factors we're going to look at in several examples of an analysis of variance today are categorical in nature, meaning that the value that factor can take is discrete. You know, type A, type B, type C, type D. But there are other cases where we might also want to introduce quantitative models, quantitative factors into our analysis of variance models. And you'll see, particularly when I talk about, for example, an analysis of covariance, that we will add a quantitative factor into the design. The factors in analysis of variance can also be crossed or nested. Probably most of the designs, experimental designs you're familiar with, are designs in which the factors are crossed. If the factors are crossed, it means we have several factors and we run experiments or collect data at different combinations of those factors. All combinations, for example, if you're doing a full factorial design. I'll show you some of that. I'll also show you some variance component designs where the factors are nested, where the levels of factor B, certain levels of factor B, are run, for example, only at one level of factor A, and different levels of factor B are run at a different level of factor A. Factors are also classified in analysis of variance as either being fixed or random. If I have several different codings I wish to compare, coding A with coding B with coding C with coding D, those are typically fixed factors. I'm really interested in comparing the levels at which I collect the data. We'll also see, though, some analysis of variance models where the factors are random, where we go out, for example, and collect 15 batches of a product, perhaps interested in the batch-to-batch difference, but not particularly interested in those 15 batches, just interested in batches as general as a sample from some larger population of batches. We're also interested, and we'll be looking today at designs in which the factors are fully randomized, where basically I assign levels of the factors randomly to the experimental units, and also designs in which the factors are partially randomized. The last couple examples I'll talk about today are a split plot design and a repeated measures design, where there's some restriction on the amount of randomization. So analysis of variance models can be quite flexible, can handle many different cases. I've selected actually 5 today, 5 examples to go through to show you and make quite concrete, if I can, these different distinctions. Now, in Statgraphics, there are 4 major procedures that you can use to do an analysis of variance. There's a one-way ANOVA. A one-way ANOVA involves a single categorical factor, where you want to know how the levels of that one factor affect the response. We have another procedure called the Multifactor ANOVA, which is designed to handle multiple factors when they are crossed. For example, a standard factorial design with several factors could be analyzed using the Multifactor ANOVA procedure. We also have a special procedure to do a variance components analysis. Now, a variance components analysis requires that all the factors, and there may be many of them, be nested one within another. And I have a nice example here of looking at moisture content in samples of pigment paste, where you'll see the nesting of those particular factors. So those are 3 special procedures, actually: one-way ANOVA, multi-factor ANOVA, and variance components analysis, that are designed for specific combinations of factors. If our data don't fit into one of the first 3 categories, then we need to use the general linear models procedure. The general linear models procedure can handle pretty much any combination of factors, any type of setup. And for example, if I needed to do analyze a split plot design or a repeated measures design, since it has some special situations, it would have to be analyzed using the general linear models procedure. Okay, now I'm going to go through examples of each of these, and the first example I'm going to do is an example of a one-way analysis of variance. A one-way ANOVA has a single factor that I'm interested in looking at. Now, I was asked last time if I could look for some financial data to use as an example, and I found on the internet a data file that was a 1/10 systematic sample of companies in the Fortune 500 list back in 1986. They went through and collected, basically took every 10th observation from an alphabetical list of the data in the Fortune 500 so that we get a sample of companies. The response variable that I found most interesting when I was looking at that particular data set was the profit per employee. You know, how much profit did a particular company make per employee, thinking that perhaps certain companies had higher profit margins than others. The factor of interest, and there's going to be a single factor in my first example, is the sector of the economy. Every company was classified as belonging to a particular sector, and the interest really is, are there differences between the sectors with respect to the profits per employee? Now, the sample data file I'm going to be looking at, and as I mentioned, you can download this from our website after the webinar is over, is a file called profits.sgd. There are about 76, I believe, companies, something like that, in the data file. We know their assets in millions of dollars of each of the companies. We know the sales. We know the market value. We know their profits. We know their cash flow. We also know in thousands how many employees work for that particular company. And finally, on the right-hand side of the file, each of the companies is classified as belonging to a particular sector, like an energy sector or a finance sector or a manufacturing sector, and so forth. And as I said, my interest is knowing whether the profits per employee vary according to which sector of the economy the company belongs to. Okay. Well, let's go ahead and actually get into Statgraphics now. Enough for my PowerPoint slides for a moment. Let's go into Statgraphics, and I have Statgraphics loaded using the classic menu, describe, compare, relate, and so forth. And I'm going to start with an empty data sheet. Now, to open up a data file, the file I'm interested in for this first example is a file called profits. I'll just ask to open up a data file, and here you can see the same data file that I showed you a picture of before. In Statgraphics, we put our analysis of variance procedures under the compare menu. Basically because what you're doing in an analysis of variance is typically comparing levels of one or more factors. And if I go to compare analysis of variance, you'll see a number of options. The first that I want to consider being the one-way analysis of variance procedure, the one-way ANOVA. Now, the one-way ANOVA data input dialog box has fields for the dependent variable and for the factor. As I said, the dependent variable is going to be profits per employee. So I'll put divide by employees. Okay, that's going to be my profits, my dependent variable. And it's actually millions of dollars divided by thousands of employees. So we won't worry exactly what the units are, but it's proportional to the profits per employee. The sector, the factor of interest that I want to compare here is sector. So I'll put in sector for the factor and press OK. Now, as in most Statgraphics procedures, the next thing you'll see is an option for different tables and graphs. By default, it's going to give me an analysis summary and an ANOVA table. That's pretty good. I also want to look here in a couple of moments at the multiple range tests. Now, as an aside, I should mention that within this particular procedure, in addition to the standard analysis of variance, it also offers you a Kruskal-Wallis test and Moods median test. Those are two non-parametric approaches to doing an analysis of variance. If you were worried, for example, that outliers might be affecting the results or worried about the assumption of normality, rather than doing a standard analysis of variance, you could do a Kruskal-Wallis test that compares the ranks, the average ranks of each of the sectors, or compare the medians using the medians using Moods median test. Now, one thing about Statgraphics, we have incorporated the non-parametric procedures directly into the parametric procedures. You know, rather than having a non-parametric section on the menu, we've simply made them options within the standard procedures where, in fact, they would be relevant. Okay, I think it's a little easier for people to find the non-parametrics that way if we simply make them options in the standard procedures. I'm also going to be interested on the graphical side in a means plot and also in an analysis of means, an ANOVA. If you haven't seen an analysis of means before, it's pretty interesting. So let's go ahead and just press OK, and that will pop up for us an analysis window. Now, up at the top left of the analysis window, you can see that there were actually 79 observations, 79 companies in this data file. These 79 companies with complete information about profits, employees, and so forth. The factor sector has 9 levels, 9 different values for sector. Now, the first thing I would typically look at when I came to an analysis of variance is in the middle left over here, and I'll maximize it so you can see it a little bit better, in analysis of variance table. As I said, an analysis of variance takes the variability in the response, in profits per employee in this case, and divides it into various components. In a simple analysis of variance, it divides it into one source of variability, differences between the groups, in this case between the sectors, and differences within the groups, within the sectors. Okay, well, I don't want to spend time discussing every number on this screen. Typically, in an analysis of variance, what you're primarily going to be interested in is on the far right-hand side, the p-value. And a good rule to remember, both in analysis of variance tables and in regression tables in Statgraphics, is that small p-values correspond to significant effects. And by small, I typically mean less than 0.05. If a p-value in an analysis of variance table is less than 0.05, then whatever that line represents is statistically significant at the 5% level. So in fact, with a p-value of less than 0.05 here, not much less, but it is less than 0.05, I would say that there are significant differences between the sectors at the 5% significance level. Okay, so we're generally going to be hoping, as we look at these analysis of variance tables, that our p-values are less than 0.05. If they're not, then at least at the 5% level, whatever is in that line of the table is not statistically significant. Okay, well, once I've determined, in fact, that there are significant differences between the groups, the next thing to look at is typically a means plot. Now, I see a little bit of overlapping of labels on the graph, so before I do anything else, I'm going to push the right mouse button, go to Graphics Options, go to the X-axis, and tell it to slant my labels. That looks a little bit better. I'm going to take that little label for sector and drag it out of the way. All right, that looks a little bit better. Let me explain what it's done. It's gone ahead and taken each of the 9 different sectors, communication, energy, finance, and so forth. Looked at all companies in each sector and computed the average profits per employee. The triangles that you see, the 9 different triangles here, are the average profits per employee for the different sectors. You can see, in fact, that it looks like the transportation sector has the lowest profits per employee, while the energy sector has the highest profits per employee. Now, in addition to showing you the mean of each sector, it's also put an uncertainty interval around the mean. The uncertainty interval shows you basically the margin of error in trying to estimate that particular mean. Certain sectors that have a lot of data, for example, the energy sector, will have rather small errors, but the communication sector, where I think there were only 2 or 3 companies, has a considerably larger margin of error. And depending upon what particular intervals you choose, you can make different conclusions by looking to see whether the intervals around each mean overlap or do not overlap. Now, the default here that came up, at least on my computer, was an LSD interval. LSD stands for least significant difference. These are due to Sir Ronald Fisher and some of the work he did on agricultural data back at the beginning of the 1900s. If you're using an LSD interval, you can take any two sectors, let's say the communications sector and the energy sector, and look to see whether their intervals overlap. If the intervals overlap, as they do here, for example, then there is not a statistically significant difference between those two sectors. So although it looks like the communications profits per employee are considerably less than those of the energy sector, there's not enough data to call that statistically significant. Now, one of the problems with LSD, though, is you can only do that for one pair. If you'd like to make lots of comparisons, as we typically do, maybe communications with energy and energy with transportation and medical with manufacturing and so forth, it's usually better to push the right mouse button, go to Pane Options, and pick some other type of intervals. The intervals I particularly like, by the way, are the Tukey HSD intervals. John Tukey developed something that he called the honestly significant difference intervals that allow you to make all pairwise comparisons, to compare all pairs and control the error rate, what he called the experiment-wide error rate, at 5%. Now, I noticed in this case that when I did that, the intervals got wider. In fact, some got so wide that they went off of the graph. Now, the easiest way to fix that in Statgraphics, if you ever change an option and you don't exactly like how it looks, if you go back to the analysis toolbar, that's the lower of the two toolbars, to the input dialog box, where you initially put the data and just press OK, it'll recalculate everything and rescale all the graphs. Just a little trick. You know, if something doesn't look quite right, you can have it rescale by going back to that input dialog box and just doing everything again. And now you can see everything's back on the screen. Now I can actually take that energy sector and look and see which of the various sectors it overlaps and which it doesn't. Energy overlaps communication, so it's not significantly different than that sector. However, I think energy does not overlap manufacturing. Therefore, I could declare actually a statistically significant difference between the mean of the energy sector and the mean of the manufacturing sector. Whatever intervals do not overlap would correspond to a statistically significant difference. Now, that's doing it graphically. Sometimes it can be a little hard to do it graphically, which is why we do it also in a tabular form. If I double-click to put that back and then go down to the bottom left to the multiple range tests, this will give you the same output but in tabular form. Now, I'll also, again, have to go to Pane Options and change to Tukey if I want to get the same analysis. And you can see here, by the way, that, well, there's two tables. The top table lists the data from smallest mean to largest mean. It also puts columns of X's to show you groups of sectors between which there are no statistically significant differences. So, for example, you can see that there's a column of X's containing everything except for energy. That indicates a significant difference between, well, that indicates that actually all of the sectors except for energy are not significantly different. They all form one homogeneous group: transportation, manufacturing, all the way down to finance. No significant differences amongst any of those 8 sectors. You can also see on the right hand, next to that, the rightmost column of X's, the one that contains energy, that it also has X's for everybody except manufacturing and retail. So in fact, the energy sector is also not significantly different from any sector except for manufacturing and retail. A nice little display that shows you where the significant differences lie. The program also lists every pair with their difference and indicates with a red asterisk which pairs have a statistically significant difference. Okay, so in fact, in this case, it appears that energy is somewhat unusual, and that it's statistically at least significantly higher profits per employee than either manufacturing or retail. Now, another interesting way to look at the same data is through an analysis of means. Down in the bottom right-hand side here, I created an analysis of means table. Again, let me slant those axes a little bit so they look better. There we go. This is an interesting chart. Another way, slightly different way of looking at the data. What this chart has done is it's taken all of the data. It's drawn a horizontal line at the average of all the companies. It's then drawn vertical lines from the average for each of the sectors to the grand average. Okay, so you can see the average of all the sectors, and energy again is the highest. It's also, though, put 95% limits around the center line, much the same as what happened, for example, in the control chart, such that any point beyond these 95% decision limits is significantly different from the grand mean. What I can see here very quickly is that the mean for energy is significantly higher than the grand mean of all the data. All the other sectors, however, are not significantly different than the overall mean, since they're all within their respective 95% decision limits. And again, the width of the limits will depend on the sample size of a particular sector. Some of these sectors have different sample sizes than others. Okay. It's an interesting plot for people, I think, who are used to looking at control charts, because it's another way to see who's significantly different from everybody else. Now, one more plot I should look at that I didn't pick up by default, and that is the residual plots. If I look at the residual plots, and again, let's slant those labels so it looks a little nicer. This plot will show you the residuals left over after the analysis of variance is performed. Now, in general, what a residual is, it's the difference between the observed value, the value in the data file, minus the value predicted from whatever model you're using. And you can see in this case there is one very large residual. If I hold my mouse down on it, it shows that it's actually row 49. Actually, if you click on a particular point and then go back to the data book, Statgraphics will highlight in blue the row that you just clicked on. And it turns out that a company called Mesa Petroleum had a profit of $167.5 million with only about 600 employees. Very high profit, obviously, per employee. Now, if you'd like to see what would happen if you remove that point, you can go back to your analysis of variance, go back to where the data was originally entered. And there's a nice little function called exclude. I don't know if you've ever used this before. but you can type in the select field of a data input dialog box the word exclude, then put a row number like 49 in parentheses, and when you press OK, the entire analysis will be redone without that particular row, without row 49. You might notice actually that if I remove row 49, the p-value in the ANOVA table becomes much more significant. And if I go look at the HSD intervals, there now are additional sectors that the energy interval does not overlap. Energy is now also significantly different than the high-tech sector and the transportation sector. These intervals got a little bit tighter once I removed the outlier. And now we can see again that energy is the basic, has the high mean here, and it's actually significantly different from now about 4 of those sectors. Okay. Well, that's a fairly simple data set. There's just one response and one sector, and one factor sector. Let's close that data file off for the moment. Go back to a brand empty data sheet and look at a somewhat more complicated example. You go back to my PowerPoint slide for just a moment and now talk for a minute about a multi-factor ANOVA. A multi-factor ANOVA looks at a single response variable as a function of several different factors. The really good book, really nice book called Applied Linear Statistical Models by Nieder, Wasserman, and several other people has an interesting data set having to do with exercise tolerance in a stress test. What they did in their particular test is they took a number of different subjects, put each of the subjects on a stationary bicycle, had them pedal, and measured how many minutes it took until they became fatigued. So the response variable in this data set is going to be the minutes until fatigue occurs on a stationary bicycle. There are 3 factors of interest. There is gender, percent body fat, and smoking history. And the question of interest is, are there significant differences in how long it takes you to become fatigued based upon your gender or your body fat or your smoking history? Well, they decided in this particular example to set up a 2 by 2 by 2 by 3 factorial experiment. They took 2 genders, obviously male and female, 2 levels of body fat, which they classified as either low or high, and 3 levels of smoking, non-smokers, light smokers, and heavy smokers. That gives me 2 by 2 by 3, or 12 different combinations of those 3 factors to look at. And at each of the 12 combinations selected 3 subjects to run through the experiment. The data file, I've saved the data and put it out on the web for you, is in a file called stresstest.sgd, which has columns for body fat, gender, smoking, and a final column for the response minutes. Okay? Well, let's go back to Statgraphics now. Call up that particular data file. It's a file called stresstest. Here it is. And you can see it's body fat, gender, and smoking. Now, in this case, the factors are crossed. And by that I mean what I've done is I've taken each level of body fat, each level of gender, and each level of smoking and collected data at all combinations. If your data looks like that, then where you want to go on the Statgraphics menu is to compare analysis of variance multi-factor ANOVA. That brings up a dialog box where you can put the dependent variable, which is minutes on the treadmill, and then the factors, body fat, gender, and smoking. Incidentally, if the factors are crossed as they are here, it doesn't matter what order you specify for the factors. There's also a field for covariates. If you had a covariate, which would typically be another variable that varied together with the response, which you could not control but at least could measure, you could actually put it in here and correct the analysis for differences in that covariate. For example, in this particular treadmill test, not treadmill test, bicycle test, other than body fat, gender, and smoking, I would hope that all the subjects in the test were identical. Well, obviously people aren't identical to one another. Hopefully, though, they're all at least the same age. Okay, if they're not, but I knew their ages, I could potentially put age in as a covariate. For example, if the smokers tended to be older than the non-smokers for whatever reason, and I didn't correct for age, well, that could bias the results. By putting age in as a covariate, I could hopefully take out some of that bias. Well, in this case, I don't know the age, so I'll just have to leave it alone. Okay. Well, what I'll do next is I'll press OK. And an options dialog box will come up, and it will offer to estimate interactions for me if I like. By default, the interaction field is set to 1. That would be only main effects. I'm going to put in a 2, which asks it also to estimate interactions between pairs of factors. I'll push a couple more OKs, and it will open up, by default, the multifactor ANOVA table. Now, the main difference in the multifactor ANOVA table is if you look at the ANOVA table down here toward the bottom left, you'll see that there are many p-values. There's a p-value for body fat, a p-value for gender, and a p-value for smoking. Actually, all three of the main effects are quite statistically significant. P-values obviously way below 0.05. There's also an interesting interaction. There's a statistically significant interaction in this data between A and C, factors A and C, which is body fat and smoking. If I say there's an interesting interaction, it means that the effect of one factor, let's say body fat, depends upon the value of the other factor, smoking. And you'll see in a couple of moments I'll show you an interaction plot, which is a very important plot to look at whenever there are interesting interactions. Before I do that, though, I want to go over and show you an interesting graph that pops up in some of the Statgraphics ANOVA procedures. It's called a graphical ANOVA. Let me double-click on the bottom right here. The graphical ANOVA is a procedure that first appeared in the classic book called Statistics for Experimenters by Box, Hunter, and Hunter. It's a way to graphically show differences amongst multiple factors after you've done an analysis of variance. Now, what it does is it basically shows you each of the factors, smoking, gender, and body fat, as well as the position of the means for each of the levels. This shows me that in general, people with high body fat lasted for a shorter time on the treadmill than people with low body fat. Now, it's done in such a way, though, that one can begin to judge whether or not differences, apparent differences, are statistically significant. What they've done is down at the bottom is a histogram of the residuals. And again, the residuals are always the difference between the observed and predicted values after you fit a statistical model. Here is the distribution of the residuals. They've then positioned the mean of the different levels of body fat and gender and smoking on lines above the residuals, where they've scaled the differences, the distance between those means, to make it comparable to the variability of the residuals. Now, the variability of the residuals is typically sigma. The variability of the means is more like sigma over square root of n. They've made an adjustment. They've made an adjustment so that if two levels are not statistically different from one another, okay, they should be within a distance that would fit easily in this residual distribution. Interpretation here is I look at the ANOVA and I say, here's low, here's high. They're much too far apart to have come from this residual distribution here. Therefore, I think they must be statistically significant, their difference. Well, P is the exact way of looking at that, and you can see the p-value on the right-hand side, but graphically you can also see it. They've also positioned males and females, and they're also too far apart to have come from this distribution at the bottom. There's likely a significant difference there as well. With respect to smoking, well, none and heavy, they're too far apart to have come from this distribution. I suspect they're significantly different. However, light and heavy, well, their distance is really within the range covered by this distribution here, so they're perhaps close enough to each other to not be significantly different. Now, you can do the same means plots in LSD and HSD intervals as you did in the one-way ANOVA, but you have to do that one at a time. You can do it for smoking, you can do it for gender, you can do it for body fat. This particular plot sort of lets you see all the factors simultaneously and get an idea of which are far enough apart, what levels to be significantly different from one another, and which are not. A nice graphical display, I thought, as an alternative to some other graphical displays in the case of a multi-factor analysis of variance. Okay. That's an important plot. An even more important plot here is the interaction plot. There is a highly significant interaction in this particular data. You might remember it's the interaction between A and C, body fat and smoking. What an interaction plot does is it takes any two levels, any two factors. For example, this one I think did body fat and gender, and plots the average response at all combinations of those two factors. So for example, this is the average time on the treadmill of high body fat females, high body fat males. Low body fat females, low body fat males. In this case, the two lines on the interaction plot are almost parallel. There isn't much, if any, interaction between gender and body fat. You notice the difference between males and females is the same at high body fat as it is at low body fat. No significant interaction between those two factors. To see the really interesting interaction, let me right-click, go to Pane Options. The interesting interaction is actually body fat by smoking, and it's particularly interesting if I put the second factor on the axis. That gives you this. Here what you can see is you can see for high body fat individuals the average minutes for heavy smokers, light smokers, and non-smokers. And you can see for high body fat subjects, smoking doesn't make much difference. On the other hand, for low body fat individuals, there's a big difference between heavy smokers, light smokers, and non-smokers. Classic interaction, the effect of smoking differs between levels of body fat. And incidentally, if you like, you can right-click, go to Pane Options, and put Tukey's HSD intervals around these as well. And basically what it's done is it's done Tukey HSD intervals for all 6 combinations. And based upon this, I could declare the non-smoking low body fat individuals to be significantly higher than any of the other 5 groups. So we allow you to put those HSD intervals on an interaction plot. Okay. Well, that's my second example. Let's see what else I have for you today. Example number 3, analysis of covariance. As I mentioned when we were looking at that stress test data, that it sometimes makes an analysis less biased, an analysis of variance, if one corrects for other factors that might differentiate between the experimental units. In general, an analysis of covariance tests whether certain factors affect the response after removing the effect of one or more quantitative factors. Now, let me make this concrete. Let's go back to that profits data I had before. Remember, I looked at the profits per employee by sector of the economy. Okay? Now, when I did that, I basically ignored the size of the company. Right? There were large companies, there were smaller companies. I found out that when I played around with this data, that profit per employee is also related to sales, the amount of sales a particular company has. And to get a good mathematical model in this case, since sales varies actually over an order of magnitude, some companies much larger than other companies, a nice covariate to look at is the logarithm of sales, the natural logarithm of sales. Now, let me go back to Statgraphics, get this data set. Let me show you what I'm talking about. Let me go File New to clear off the data sheet and load back again that data file I had on profits. Here it is. Let me show you just a quick XY plot so you know what I'm talking about. Let me go to Plot, Scatter Plots, XY plot. On the y-axis, let me put profits divided by employees. But now let me put the log of sales on the x-axis. And we'll get a much better picture, actually, if we also exclude row 49 the way we did before. Okay. Let's press OK. And here's what the picture looks like. Here's a picture of the profits per employee on the y-axis versus log sales on the x-axis. And I think you can see that as the log of sales goes up, the profits per employee goes down. So that there's some correlation between the log of sales and profits per employee. Well, the problem with that would be if I wanted to compare companies in different sectors, like companies in the energy sector with companies in the transportation sector. If there was much difference in the average size of the companies, the average sales of the companies, that variation in sales could affect my comparison of the different sectors. In an analysis of covariance, what I want to do is basically take each of the companies and correct it back to some average value of sales so that I can remove the relationship between profits and sales before making a comparison amongst the different sectors. In Statgraphics, to do that sort of analysis of covariance, you need to go to Compare, Analysis of Variance, Multifactor ANOVA. Now, it's just going to be a one-way ANOVA with a covariate, but you need to do it by selecting the multifactor ANOVA. The dependent variable is going to be profits per employee. The factor will be sector, exactly as I've done before. Now where it says covariates, though, I'm going to put in the log of sales. And again, to get a good result, I'm going to exclude row 49 from the calculations. Okay. Let me now press OK, OK, and I'm going to be particularly interested in the means plot. Actually, here's the means plot now, having done the analysis of covariance. So let me fix the labels. Let me switch it over to 2 keys intervals. And let me do it one more time here to make sure all the intervals are on the screen. Here's your picture. Now, I don't know if you can see it, but what it's plotting is what are called adjusted means. In the original analysis of variance, the one-way ANOVA, each of the diamonds was located at the average profits per employee amongst all companies in a particular sector. In an analysis of covariance, what you do is you first adjust all of the data essentially back to an average level of sales. And what gets plotted on the means plot here is what are called the adjusted means. So for example, if the energy companies in the energy sector tended to be large, have high sales, okay, their numbers would have been adjusted up a little bit because profits tend to be low in very large companies. And if transportation happened to be small, they would have been adjusted the other way. You can now, though, do the same comparison. I still see significant differences between energy and finance, energy and manufacturing, energy and transportation. Their intervals still do not overlap. The important thing is, though, I have a more powerful analysis, a less biased analysis, because I've adjusted out the possible effect of sales on profits before doing the comparison of the different sectors. And you can see from the data input dialog box, you could put in more than one covariate if you needed to in doing this multi-factor ANOVA. But I thought that was an interesting example. They didn't change much. The correlation between profits and sales wasn't huge, okay, but it was enough to give you, I think, somewhat different conclusions if you looked at the data. Okay, that's my third example. Now, my fourth example will be a variance component study. Up until now, basically what I was interested in when I looked at the factors was what would happen to the response variable if I changed something, if I changed the sector, if I changed the level of body fat. There are other cases where one really doesn't want to make changes. Okay, changes just happen even though you're trying to produce the same product over and over again. And in those cases, it can be very interesting and useful to do what's called a variance component study. Now, I'm going to talk about an example from a book called Statistics for Experimenters by Box, Hunter, and Hunter. It has to do with the manufacturing of pigment paste. Okay. The manufacturer here was actually getting complaints from the customer that every time they opened a can of the pigment paste, they were never sure how moist it would be. Sometimes it would be overly moist, sometimes it would be too dry. So the experimenters were interested in knowing where that variation was coming from. So what they did is they did a classic variance component study. They took, I'm sorry, let me go back. They took 15 batches. From each batch, they took 2 samples, and on each sample, they ran 2 tests. It's called a 15 by 2 by 2 hierarchical design. They went out, they collected 15 batches, 2 samples from each batch, 2 tests on each sample, with the goal of knowing how much of the variability they're observing is due to differences between the batches, how much is due to differences between samples within a batch, how much is coming from tests made on a particular sample. Okay. Now, the interesting difference, one of the interesting differences in this case, is that the data are nested. The factors are nested. If I show you the data file, and here's the data file, it's called pigment.sgd, you'll notice that there are, if you scan down the file later on, 15 different batches. 2 samples were taken from each batch. So you see sample 1 and sample 2 apply to batch 1, sample 3, sample 4 apply to batch 2. And then 2 tests were run on each sample from each batch. With this sort of a structure, we say that test is nested within sample, which is nested within batch. And the measurement that's made is the moisture content. Now, let me show you how this operates. It's fairly simple. Let me close this off and open up that file. That file is called pigment. Here it is. Batch, sample, test, and moisture. If you have a data file like this, where all the factors are nested, test is nested within sample, sample nested within batch, you can use the compare analysis of variance components procedure. Now, the variance components analysis dialog box has a space for the dependent variable, which in this case is moisture, has a field for the factors, and the factors in this case are batch, sample, and test. Now, one thing to watch out for in this case is that the factors, batch, sample, and test, if they are nested, have to be specified in the order of nesting. In my stress test, my bicycle test, it didn't matter what order I put them in. But in a variance components analysis, you have to put them in the order of nesting from the top down. So you have batches, samples within batches, and tests within samples. Okay, in that case, you can just do an OK, and so forth, and you'll come up with one graph and one table by default. I'll show you a graph real quick. It's called a variance components plot. What the variance components plot has done is it's taken each of the 15 batches, okay, and plotted actually a little blue horizontal line at the average moisture observed in each of the batches. And you can see there's quite a bit of variation from one batch to another. There's a batch that averaged about 35, another batch down here that averaged only about 18. The plot has also taken each of the 2 samples from each of the 2 batches and drawn a line from the average of the sample down to the average of the batch. Now you can see that there are some batches like batch 5 where the samples were quite similar. There were other batches like batch 15 where there was a very large difference between the 2 samples. Here's one at about 38 and one at about 26. So you can see, I think, just graphically that there's quite a bit of variation between the batches, but there's also quite a bit of variation amongst samples within a batch. Now, the primary goal of this type of study is to figure out where the variability is coming from. And the analysis of variance table for the variance component study gives you a line for each of the factors. for batch, for sample, and for test. And on the rightmost column shows you the percent of overall variation coming from each of the factors. And the major problem they discovered in this particular data set was variation amongst samples within a batch. 78%, it says, of the overall variation in the data appears to be coming from samples within a batch. 20% of differences between the batches, 2.5% due to the testing process. The majority, though, coming from variation between samples within a batch, which has always led me to believe that perhaps they weren't mixing the batches up well enough. Okay, so if they drew a batch, sample from one part of the batch, it was considerably different than if they drew it from a different part. Don't know, but I've always thought that that might be the reason that there'd be a large difference. It's a variance components analysis. Differences basically are that we didn't really try to change the batches. We knew the batches were going to change, but we had no particular interest in one batch versus another. Secondly, the samples are nested. The specific tests came from specific samples, which came from specific batches. Okay. All right. Well, that's also an interesting example. Now, let me go on to something a little bit more complicated. As I said, under the compare menu in Statgraphics, you have procedures, several procedures, that have to do and are designed to handle common situations. A one-way ANOVA, a multifactor ANOVA, a variance components ANOVA, where there's no particular restriction on randomization. When we ran, for example, the bicycle test, we randomly picked people out of the population. Okay, and gender was randomized in the same sense that body fat was, that smoking history was, and so forth. In practice, there are cases where some factors are hard to change. And if they're hard to change, we may not want to randomize them as often as other factors. Now, that leads us into a number of different types of designs, the most common of which is called a split plot design. Split plot, the word split plot came from agricultural uses, where if they were studying, for example, the differences between different variety of wheats and different fertilizers, they might take a farmer's field, divide it up into big plots, randomly assign varieties of wheat to the big plots, and then take each big plot, divide it into small plots, and randomly assign fertilizer to smaller plots. The same sort of thing happens sometimes when you're doing industrial experiments. And there's an interesting example that Box Hunter and Hunter talk about having to do with studying different coatings that could be placed on steel bars in order to improve their resistance to corrosion. Now, I'm going to show you this, this data and how we analyze it in Statgraphics. And basically, the response is going to be corrosion resistance of steel bars. There'll be two factors, furnace temperature and coating. And what's going to happen, you see, we're going to take a steel bar, we're going to put a particular coating on it, we're going to put it in the furnace, and after some amount of heat is applied, measure the resistance to corrosion. Now, the problem here, though, is certain factors, one factor in particular, furnace temperature, is hard to change. I mean, ideally, you would think, what would you do? Well, you'd pick a steel bar, you'd randomly assign a coating to it, and you'd randomly assign a furniture temperature. So you'd take the steel bar, you'd put on a coating, you'd heat the furnace to a certain temperature, and measure the corrosion resistance. You'd then pick another steel bar, randomly pick a coating, randomly pick a furnace temperature. But, you know, if you had to heat the furnace up to a particular temperature over and over and over and over again, it could be very time-consuming, very costly. Instead, what was done in this case is what's called a split plot design. What they decided to do was do a total of 6 runs of the furnace. During the first run, the temperature setting would be 360 degrees. Okay. During the second run, 370 degrees. During the third run, 380 degrees, and so forth. So they'd shut the furnace down, and then they'd bring it up to a particular temperature. Once they brought it up to a particular temperature, they'd put 4 bars in the furnace, each with a different coating. And they would randomly decide which coating was placed at which position in the furnace. Now, the 2 interesting factors here are coating and temperature. However, the amount of randomization that's being done is different for the different factors. The only time that temperature is changed is when they go from one run to the next. Okay, so really for looking at the effect of temperature, I really have only 2 runs at 360 degrees, 2 runs at 370 degrees, 2 runs at 380 degrees. Now in split plot terminology, each run of the furnace is a whole plot. Temperature is a whole plot factor. It stays the same throughout that whole plot. On the other hand, coating is randomized each time they do a run. Okay, and each position in the furnace is called a subplot, and therefore coating is called a subplot factor. Now, the important thing statistically is what's going to happen is when I look at differences amongst coatings or differences amongst temperatures, they're subject to different levels of experimental error. If I look at the difference, for example, between C2 and C3 and C1 and C4, the only source of variation here amongst these 4 experiments, for example here, is the position difference. On the other hand, when I look at this 360 versus this 360, the difference that I'm going to be seeing is the difference between runs, whatever variability there is. If you cool the furnace down, bring up to 360, cool it down again, bring it back up to 360. Temperature is not changed as often as coating. The experimental unit is larger, and therefore it's likely to be subject to a larger amount of experimental error. Well, what's the problem? Well, the problem is if I just used multifactor ANOVA and didn't take account of the fact that temperature was not randomized across all 24 of the bars that I'm looking at, the results, the statistical tests and intervals for temperature would be wrong. Temperature is likely to look, if I just put it through multifactor ANOVA the way I did with the bicycle test, temperature is likely to look much more significant than it really should. I need to take account of the fact that temperature was not randomized each time I tested a steel bar, whereas coating was changed every time I did. Okay? So we've got whole plots and subplots. Well, what's the proper thing to do? How do I analyze this? Well, first off, I'll show you what the data file looks like. I have a data file out there called steel bars. Okay? It has a number of different columns in it. It has one column for run of the furnace. That's the whole plot. And there were 6 runs of the furnace. There's a column for the amount of heat that was applied during each run. either 360, 370, or 380 degrees. There's a column indicating the position in the furnace where corresponding to each row of my file. Okay, there's a column called coding indicating what coating was applied to the bar at a particular position in the furnace. And then there is the corrosion resistance, the measure. Okay, now to analyze this, we're going to have to use the general linear models procedure. As I said at the beginning of the seminar, if it doesn't fit one of the special cases that the other three procedures under compare will analyze, then I need to go to compare analysis of variance general linear models. Whoops. Actually, I need to load the data first. I don't have any data. I won't be able to do much of an analysis. Let's load the data. It's in a file called steel bars. Now, to analyze the data, I'll go to compare analysis of variance general linear models. The dependent variable is the corrosion resistance. The factors of interest, the categorical factors, are first the heat. Secondly, the run of the furnace. And now this is the first thing that's a little bit different here. If I have a split plot, I'm going to have to compare temperature against variations amongst the whole plot. So I need to put in, as a factor, a column that distinguishes the whole plots. Okay. And then finally, the third factor will be coding. Okay, so I have as my factors the heat setting, what temperature am I at, which run was it, and what coating did I apply to the bars. The GLM procedure also will ask you to specify the model that you want to fit. And by default, it'll put in a letter for each of the factors. That corresponds to the main effect of the factors. Well, let's see what we want to analyze. The first thing we want to analyze, obviously, is heat. I want to know differences between 360, 370, and 380 degrees. You'll also notice on the far right-hand side of this dialog box a section to indicate whether or not a factor is random. A factor is random if it's one of many levels that could have been picked from a larger population. Well, heat is not a random factor. It's a fixed factor. 360, 370, 380. I'm really interested in those temperatures. As far as run of the furnace, on the other hand, run of the furnace is a random factor. Okay, I could have done many, many, many runs. I'm not particularly interested in one run versus another, although it does have some impact on the results. Also, factor B is nested within factor A. It's necessary in fitting this split plot here that I type B, open parens, A, close parens. That tells it that run of the furnace is nested within heat. For example, runs 1 and 4 are only done for 360 degrees. Runs 2 and 5, they're only done for 370 degrees, and so forth. Factor B, run, is nested within heat. We don't do run 1 with every heat. It's done only with a particular heat. Coding is a factor, and it's a fixed factor, and I'm also interested in an interaction between A and C, coding and heat, and those are crossed. I've done all combinations of A and C, all combinations of those two factors. So that's the proper setup, and if I then press OK, it'll offer me a number of different tables and graphs. Press OK again, and up will pop the analysis of variance table. Of particular interest here is or what are called the type 3 sums of squares. this table right here has a table that indicates whether or not a factor is statistically significant. And in fact, there is not a significant main effect of heat. You may be able to see that over here with the means plots. On average, there is no significant difference actually between 360, 370, and 380. You can see that from the means plots. However, there is a significant difference, so it says, amongst the coatings. And there also is a significant difference or a significant interaction of heat by coating. Now, if I scroll down a little bit, I should also point out one other table, something called variance components. I indicated when I talked initially about a split plot design that in a split plot design, there are whole plots and there are subplots. And the variability between whole plots is often considerably greater than the variability between subplots. In this variance components table, you see the estimates of the variance components between runs and residuals being what's left over. That's the subplot error. And in fact, in this case, the whole plot variance is almost 10 times the subplot variance, meaning I'm getting a much better, more powerful test of coating, the subplot factor, than I am of heat, which was only varied across the whole plots. Okay. Well, if you really want to see the story on this data, you need to ask for the interaction plot, though. Let's ask for the interaction plot. What you see here is a plot of the corrosion resistance for every combination of heat and coating. Right? You see the 4 coatings at 360, the 4 coatings at 370, and the 4 coatings at 380. Particularly notable here is that really 370 and 380, those 2 levels of heat don't show much difference except for coating 4. The real winner in this particular case obviously is coating 4 at 380 degrees. And again, if you like, you can always go in and add on HSD intervals. And in fact, the interval around that highest corrosion resistance doesn't overlap anybody else, indicating there is a significant difference between the resistance I'll get using coating 4 and 380 degrees and any other combination of the factors. Okay. That's an example of a split plot and design, and the trick in the analysis, I will remind you, is that you get the model specified properly. And that is B nested within A. Example, and then I'll take some questions. This example will be a repeated measures design. Now, a common type of variation on the standard analysis of variance comes up when repeated measurements are taken on the same experimental unit. Happens a lot, for example, in drug trials. And here's an example that I pulled out of a book called The Analysis of Messy Data, which is by Millikan and Johnson. It was an experiment in which there were 3 drugs: the AX23 drug, the BWW9 drug, and a control. All of which were expected to have some impact on a patient's heart rate. What they did then is they selected 8 patients at random. Well, 24 patients at random. 8 they gave the first drug, 8 they gave the second drug, 8 they gave the control. They then measured the heart rate of each of the patients at 4 different times. Time 1, time 2, time 3, and time 4. Okay? Now, there are some similarities between this repeated measures design and a split plot design. One is that subjects are nested within drug. Right? You have different subjects given each of the drugs. So the drugs are simply randomized across the subjects. Time, on the other hand, there are 4 measurements made on each subject. So time is changed more often than drug. It has basically the same setup as a split plot, where drug would be the whole plot factor, time would be the subplot factor. There's one difference, though, and that is I can't randomly make assignments of time. In the split plot design, I actually took each steel bar and randomly put a particular coating on a bar, but randomly positioned it in the oven. Here I can't randomly position the times, because the times are actually, immediately after the drug, 15 minutes later, 30 minutes later, 45 minutes later, whatever it happened to be. However, under certain conditions, having to do actually with the covariances of the differences between the times, one can analyze the data in much the same way as you can a split plot design. Millikan and Johnson actually have excellent discussions of when you can and when you can't do the standard split plot analysis on a particular data set. And there are certain tests that you can run on a particular data set to see if what they call the standard analysis can be done. We're doing some work on that, incidentally, for the next version of Statgraphics. Right now, though, I'm going to assume that the normal way of analyzing this is appropriate. So I'm going to take this data, load it up into Statgraphics, and do the analysis. So let's, again, put a new data sheet up, and let's load a data file. This file is called heart rate. To do the analysis, I'll have to go again to the general linear models procedure. And this will be very similar to how we did it with the split plot design. Heart rate is a dependent variable. Factors of interest are drug, subject, and time. Okay? Drug is a fixed factor. Subject is a random factor. Time is a fixed factor. Subjects are nested within drug. A subject gets only one particular drug, so they're nested within drug. And I'll also ask, as I did before, for an interaction between the two fixed factors. Same basic setup as the split plot in terms of the model. Let's take the standard analysis here. And again, of interest is the type 3 sums of squares. In this case, everything is significant. You see a significant difference between the drugs, a significant difference due to time, and it's also a significant drug by time interaction. Now, I'm going to use this example actually to show you a couple other things, though. Let's go down here to the means plot. Here you see the three drugs, AX23, BWW9, and the control. You see a little diamond at the average result for each of those factors. Around each of the factors is by default an LSD interval. Well, let's see what happens if I right-click and go to Pane Options. Okay. if I right-click and go to Pane Options, I see I can do LSD intervals or HSD intervals if I want. I'm sorry, I actually didn't want to go to the plot. I wanted to go to the multiple range tests. Remember, multiple range tests gives you the same information as the means plot, but it gives it to you in tabular form. Here we are. Yes. It shows you here the 3 different drugs, the control, AX23, BWW9. It then shows you what's called a table of contrasts. Right now, contrasting AX23 with BWW9, AX23 with a control, BWW9 with a control. A contrast is basically looking at the difference between the mean of one drug and the mean of another. Well, there are special ways to handle the comparison if, in fact, there is a control. If I press the right mouse button and go to Analysis Options, you'll see that one of the options in the GLM is to compare all pairwise means. A second is to do a comparison against a control. Okay. Now, if you do have a control, and what you really want to do is test whether a particular drug is better than a control, you can get a better comparison, a more powerful comparison if you restrict yourselves to just comparing the levels of the factor to the control. So if I set this to versus control and choose Dunnett's method, which is a method particularly designed to compare things to a control, and tell it that the 3rd level in my experiment was the control, you'll see what it will do is it will now compare AX23 with the control and BWW9 with the control, indicating with an asterisk that the only drug significantly better, or different actually, than the control is BWW9. So one of the additional settings that GLM has that the other ANOVA procedures don't have is the ability to compare everybody against the control. And that can actually be more powerful than doing, for example, Tukey, where you do all pairwise comparisons. You can also do your own contrasts. There's a space here for doing a user-specified contrast. And what I could do, for example, is I could ask it to compare the average of AX23 and BWW9 against the control. If it's a user-specified contrast, then it allows you to actually develop a contrast, like take half of my first level, half of my second level, and compare it -1 against my last level. And that will do what's called a user-specified contrast. Now, I've actually written that out in my PowerPoint slides for you to see later on. A user-defined contrast would be something like take half the mean of the AX23 drug, half the mean of the BWW9 drug, and compare it against, subtract it from the control, and tell me whether or not that's significantly different than 0. What you're really doing is comparing the average of the 2 drugs against the control. And I put in 0.5, 0.5, -1 in the second dialog box after specifying that it was a user-specified contrast. And again, the asterisk here indicates that it is statistically significant at the selected level, which was the 95% level. Okay. Oh, one more plot I guess I should have showed you. That's the interaction plot. Last plot of the day, interaction plot. This will actually show you the 3 controls and the 4 time periods. It's best if I go to pane options and switch the factors around, though. Here you go. This is a very interesting plot. You've got your 3 drugs, AX23, BWW9, and the control. You see the observed heart rate at the 4 time periods. In the case of the control, very little changed. Drug AX23 was low at first, then it was high for 2 periods, then low again, whereas BWW9 was high at all 4 time periods. Remember, there was a significant interaction between drug and time, so the interaction plot's quite important. All right, well, that's about all I had time for in terms of the analysis of variance using Statgraphics. Hopefully you found some of those examples interesting. I have on the last page of the handout, the PDF file that you can download, the various references from which I drew data, the box Hunter and Hunter book called Statistics for Experimenters, from which I pulled that split plot example. Nice discussion of split plots. The data and story library maintained by CMU has a lot of good data sets. I pulled that company data set from there. Milliken and Johnson, their analysis of messy data. I pulled the split plot, the repeated measures design from there. And finally, Nieder, Wasserman, and the rest of the folks applied linear statistical models. Just a great book on the analysis of variance. Okay, well, I see we still have almost everybody with me from when we started, which is always makes me feel good. Let's see what we have in terms of questions that might have been submitted. Well, so far I have 11 questions. This should be fun. I'll stick here as long as necessary. The first question, question number 1. A reliability webinar would be useful for our company. Is there any built-in way to do accelerated aging? Okay. In Statgraphics, there are a couple places that you can go to do accelerated life testing. Under the life test section, there is a procedure called an Arrhenius plot. That is a plot that is intended to help you do acceleration, where acceleration is by temperature. A lot of chemical processes can be studied by subjecting the items under test to higher temperatures than would normally be experienced. So there's a section on Arrhenius plots. There's also, under the Relate menu, a parametric models procedure that can be used to do accelerated life testing. I'm going to definitely do a webinar to show you those 2 procedures and how they can be applied, and talk about life testing and accelerated life testing in general. Those are the 2 places to go right now, and if you look at the PDF files for those 2 procedures, the Arrhenius plots procedure and the life data parametric models, you'll see some examples actually of some accelerated testing. Second question, is it safe to say that a p-value is the probability that the differences you see are due to chance? Depends whether you're a Bayesian statistician or not. I like to think about the p-value as being the chance that I would observe differences as great as I see if there was nothing going on. So basically, the way you phrased it, a p-value is the probability that the differences you see are due to chance. I would say, yes, that would be a fine interpretation unless you were real strict about the interpretations of p-values. The classical statistician would say that there either is a difference or there isn't. You can't attach a probability to an event that's already occurred. But if you're a little bit more liberal on your interpretation, a p-value is the probability that the differences you see are due to chance. That's not a bad statement. As I said, I usually think about it more like, what's the chance I could have gotten the outcome that I'm looking at if there really were no differences? And if that probability is small, then it's likely that there really are differences. Someone also asked about the rescaling. Yeah, occasionally when I make a change, I change an option. I go to pane options, for example. It might add intervals and for some reason not adjust the y-axis automatically so that the intervals fit. I don't know. What would happen if I put HSD intervals on this? Well, in this case, they all fit. But you saw one time when I did it, they didn't all fit. If you go back to the leftmost button on the analysis toolbar, it's the input dialog button. And you press OK. That always forces the procedure to recalculate everything. And when it recalculates everything, it'll always rescale. So one thing I sometimes try, if I think this scaling is not what I would like it to be, before I manually go in and use graphics options to rescale it, I'll try pushing that input dialog button and see if it doesn't rescale it for me. So it's that leftmost button on the analysis toolbar. Fourth question, why does transportation have two X's? Okay. Yeah, that little diagram can be a little bit confusing at first. I think what was being referred to here was in my profits data. Okay. Remember, we did a one-way analysis of variance, profits per employees by sector. Okay. And that when I asked for a multiple range test, it came up with a diagram something like this. Oh wait, let me switch it to 2 keys so I have what I had before. There was a question here, why does transportation with a mean of 0.429 have 2 X's? The way you interpret this result is, you see the first column of X's. Just look at the first column. Everybody except energy has an X in the first column, meaning everybody but energy form a homogeneous group within which there are no differences. Okay. If you look at the second column of X's, you'll see that everybody except manufacturing and retail has an X in the second column. Everybody except manufacturing and retail also form a group within which there are no significant differences. Now, transportation actually has an X in both columns because it's not significantly different than anybody. And you could probably see that in the means plot. Transportation, primarily because it's so big, the interval is so big because the sample was so small. Transportation overlaps everybody. It overlaps energy, it overlaps finance, it overlaps everybody. So it's not significantly different than anybody. It belongs to both groups, if you like. Well, it doesn't really belong to both groups. It's not significantly different than anybody in either of the groups. So that's the problem, and it's, I guess, partially due to the fact that it's transportation. Oh wait, transportation. Yeah, I gotta get these up to their HSD intervals. Yeah. Okay, here we go. I'm looking at communications. Transportation. Yeah. See, transportation also, yes, it does. It overlaps everybody. Transportation overlaps all of these guys, overlaps this guy, and overlaps this guy. Yeah, and transportation actually had 6, but again, it's not significantly different than anybody. The only real significant differences are energy in manufacturing, energy in retail. They're the only pairs that don't have an X at the same time in any of the columns. The only 2 significant differences on this particular page. Question 5. Is one justified in removing the outlier using the exclude option? Is this not selectively manipulating the data? Absolutely, it's selectively manipulating the data. I did it, you're right, without any real justification, mostly to show you how the exclude function works. Before I do take out a particular observation, row 49, I should have a real justifiable reason to treat it separately. Yeah, I pulled it out because I didn't like the way it looks, I suppose. No, more, I wanted to show you how to use that exclude function. You know, when I first tried it, I was thinking that, you know what, maybe the fact that energy is different, and then I'm getting a statistically significant result here, is entirely due to that one data value. I actually thought that if I removed row 49, that energy might not be significantly different than anybody anymore. I was actually surprised when I first went back here, put in exclude 49, to see that if I excluded that point, which was the highest energy value, the company with the highest energy profits, then energy became more significantly different. There were more differences, and the p-value was lower than before. Often, if you remove an outlier, everything comes back, you know, to, and things are not significant when they were before. So after I saw that removing the outlier actually made things more significant, I thought that it would be a good thing to illustrate. But yeah, you're certainly valid in criticizing me for pulling it out arbitrarily without a real justification to do that. For example 2, does it make sense to report significance for main effects if interaction effects are significant? Let me pull that multifactor ANOVA up again. Where was it? It was stress test, right? Analysis of variance, multifactor ANOVA. When I did this particular example, and I put in the interaction, okay? We saw an analysis of variance, and in the analysis of variance there were significant main effects, and there was one significant interaction. Okay. The question is, does it make sense to look at a comparison of main effects if there is a significant interaction? And I would say no. If two factors interact, if body fat and smoking interact, then it doesn't really make sense to compare the main effects of the factors that interact. For something like gender, though, that does not interact, it does make sense to look at the main effects. So if I go over and look at a means plot, it would not make much sense to look at a means plot for body fat because that interacts with smoking. And you'd get a misleading picture if you just looked at that. But if you took something like gender, which doesn't interact, then it's reasonable to look at a comparison of the main effects for factors that don't interact. And the only difference between the one-way ANOVA and here is basically the residual error. When you create these intervals, it's based upon the residual mean square. So if I did just a one-way analysis of gender, didn't account for body fat and smoking, the mean squared error for the residuals would be much larger, and therefore the intervals would be much wider. For ANOVA under select, how do we exclude multiple data sets? I guess I knew you were going to ask me something like that. Let's call up that same data file, that profits data file again. Where I had gone in and did a one-way analysis of variance. Profits per employee, right? According to sector. I had initially said exclude 49. What I didn't show you, though, is that if I do exclude 49 and look at the residuals, oh, there's another large residual. Now it's row 25. What if I want to exclude row 25 also? Okay, well, what you have to do is you have to say exclude 49 and, that's an ampersand, exclude 25. That should exclude both row 49 and row 25. Yeah, it's not commas in the exclude function. Exclude just takes a single number. But you can connect two excludes with an and, I think. Let's see. Yep, it did it. Exclude 49 and exclude 25, and it took out both. Now they really look clean. I wonder what the means plot looks like if I take out both. Whoa. Oh, well, let's make them HSDs. Yeah, you can see the intervals are even tighter. Now energy is significantly different than almost everybody except communications. So you can use exclude with the ampersand. Are the demonstrated statistics available in version 15? I'm trying to think if there's anything not in version 15. I actually think that everything I showed you today is the same in version 15 as in version 16. We really did not change any of these analysis of variance procedures in 16. So I'd have to say I think 15 and 16 work identically with respect to everything I showed you today. In doing ANOVA in your program, I will occasionally see red font numbers in the multiple range tests. However, the homogeneous groups column shows all single X's, meaning not significant. P-value is also greater than 0.05. Why does the difference column say there are significant differences? Well, one of the things about the multiple comparison procedures, what you get under multiple range tests, is that they should not be used unless there is a significant p-value in the ANOVA table. Because of the fact and the way that they're done and the way they handle probabilities, they really shouldn't even be looked at unless the p-value in the ANOVA table is significant. In fact, I have a nickname for the p-value in the ANOVA table. I call it the "Am I wasting my time" test. Because unless this particular p-value here is less than 0.05, I'm not justified in looking either at the multiple range tests or the Tukey's or the LSDs and so forth. They are meant to be used only when there is a significant result in the ANOVA table. Why you might see a single column of X's and still see significant differences, I don't know. If you can send me a data set with that, showing that, I'd like to see it. I have not seen that myself. 10. In designed experiments, there can sometimes be nested factors. How do we take nesting into account while using DOE, or do we do the GLM procedures? The DOE, what we have under the DOE section with the experimental design wizard, the legacy DOE procedures and so forth, all of the analyses currently assume that the factors are crossed. If you have something like a split plot that you set up or a repeated measures design, it should not be analyzed under the DOE section. It should, as you suggest, be analyzed under the general linear models procedure. Okay. We do intend at a point in the future to put additional designs into the DOE section, special split plot and repeated measures designs. Go to statgraphics.com, resources, how-to guides. At the very bottom, you'll see some additional tutorials. For GLM, do you report significant main effects when interactions are significant? Well, really, if an interaction is significant, it means that that factor, whatever factors are involved, have a significant effect on the response. And in fact, if there is a significant interaction, then the main effects are really irrelevant, and so I would say probably no. Okay, although you can indicate that the main effects are significant, but the interactions basically trump the main effects. A suggestion for the autumn session: doing some conjoint analysis with multinomial logit models. Well, I guess you're going to want me to do some work over the summertime to put that together. I will take that into consideration. Conjoint analysis with multinomial logit models. I'm not going to do that one off the top of my head, I'm afraid. Question 14. How do I account for data over time like quarters, annualized data? Is it a category, or do I quantify this as 1, 2, 3, etc.? Yeah, well, there are a number of interesting examples of actually repeated measures designs where the data might be quarterly data. You look at a performance of a particular company, quarter 1, quarter 2, quarter 3, quarter 4. Those are repeated measurements taken on the same company. So truthfully, data like that could be handled in a similar fashion to the data for the repeated measures example. Remember this particular example here where I might have different companies from different sectors of the economy. And then I could have Q1, Q2, Q3, Q4. I actually looked for some data like that in doing this repeated measures example, but didn't find a good example in any textbook that I had. But it could certainly be handled as a repeated measurement, the same way I handled the data here in the repeated measures design. And whether you label it 1, 2, but the other question I see is, do you handle it as categorical or as 1, 2, 3, 4? Well, if you put it in as quantitative, 1, 2, 3, 4, rather than like T1, T2, T3, T4, and handle it as a quantitative factor, then if you only put it in as a main effect, it would assume a linear trend over time. So it sort of depends. Quarterly data could be handled either as a quantitative, 1, 2, 3, and 4, in which case you might force it to have a linear trend over time, but a more general approach would be to handle it here as categorical. Hi, I've been told that the data from my master's will require a time series analysis. It would be nice to have a webinar on that. Yeah, I'd like to do that myself. I'll definitely do that in the fall. What comparison test do you recommend for a very large number of comparisons? Whichever one gives the tightest intervals. I'm not sure exactly what to say on that. But one thing Statgraphics certainly does make it easy for you to do, for example, if you're doing some multiple range tests, is to try different comparisons. You see, for example, here, let's just take this particular data set here. Using an LSD procedure, energy and finance are significantly different. And the rest of the table here says that if I look at energy and finance, the difference is 18.1 plus and minus 6.97. If I switched over and tried Tukey, it's plus and minus 11.2. If I switched over and tried Chaffee, it's plus and minus 14.2. I think the question really is, what are they meant for? LSD is meant for doing single pairwise comparisons at a fixed level of confidence. Tukey allows all pairwise comparisons. Chaffee and Bonferroni allow all comparisons, not only pairwise comparisons. And then Student, Newman, Cools, and Duncan are somewhat different. They actually do things somewhat differently. The one that I typically do, since I'm typically just concerned myself with comparison between pairs, is Tukey's procedure. It'll be tighter than Chaffee and Bonferroni, but it only allows you to do comparison between pairs of levels, which is enough unless you're doing your user-specified contrasts. If you're doing special user-specified contrasts, for example, half of this level plus half of this level minus this level, then you can get tighter comparisons if you use Chaffee and Bonferroni. A good discussion of this is that Millikan and Johnson book, a discussion of all the different methods. They have a lot more experience, I must say, in multiple comparisons than I do. So I would push you to look at Millikan and Johnson for a comparison of the different tests. Is there a way of setting options and making them persistent? In your presentation, you kept asking for the labels to be slanted. Well, yeah, I could have done that. If I have a particular change that I want to make and have it persist, okay, I can right-click, go to Graphics Options, go to X-axis, for example, make things slanted, and say Apply. Remember I kept doing that? Okay. If I wanted that to be the new default, if I make a change to a graph and want that to become the new default, I can go to Graphics Options, go to Profile. And then if I pick a particular profile like user number 7, tell it I want that to be the default, and say Save As, and call this Slanted Labels, for example, I can create myself a graphics profile with slanted labels. So the next time I did a plot, let me just do something real quick. Cash flow, for example, by sector. Hopefully the graphs will come up with slanted labels. There you go. Now slanted labels is the default. Problem is, of course, it's the default on all the graphs, which it may not be what you want slanted label on all the graphs. But yes, the answer is if you make a change like slanted labels using graphics options, you can go to the Profile tab and actually create a user profile. And if you like, make it the default that will remember slanted labels as the way you like the labels to be. HSD or Duncan. Okay. Yeah, that had to do with the multifactor ANOVA, right? When we were doing a multifactor ANOVA, which procedure did we want to use when we were doing multiple range tests? It's two different ways. People prefer different things. I usually do the HSD. Some people do like Duncan instead of HSD. I have to tell you offhand, I don't remember exactly what the advantage of Duncan is, but I do have my Milliken and Johnson book here. Let me open real quick to Duncan's method. And see what it says here. Not really. Well, I'm not finding it real quick. I have to research that. Duncan, I don't remember off the top of my head exactly when that is best, to be honest. Please consider a topic on the webinar a webinar on the topic of forecasting. Yeah, that would be fun, wouldn't it? I'll definitely consider that. Question 21. This is a busy day. Can we simulate some GLM procedures in DOE by using blocks to take unspecified differences, interactions into account? That's an interesting question. What you might notice on something like this split plot, go back to the split plot for a moment, is that the run of the furnace is basically like a block. The problem here, though, is that only one temperature setting is run in each block. Can we simulate the GLM procedures in DOE by, I don't know, I'd have to give that some more thought. I don't see that immediately. Okay, somebody else wants a time series webinar. Okay, 3 votes for time series. We'll definitely do a time series webinar in the fall. Well, I thank everybody who's stayed around for the webinar series. We've had pretty sizable audiences, so I definitely feel like it's been worth doing. We'll schedule some more for the fall. Meanwhile, we'll take the recording of this particular session and put it up on the internet so that you all can download it or pass it on to someone else if you think it was useful. Again, I thank you for your patience. That was over 2 hours, but hopefully you found it informative. Don't forget to send me directly also any comments. You can send them to support. They usually get sent on to me, but you can also send comments to Neil at statgraphics.com, and I'll see them. Okay, until the fall, have a good day.